Chapter 2.7, Proving Segment Relationships. In Chapter 1, and also in this chapter, we have used the segment addition postulate. What the segment addition postulate tells us that if we have a segment, let's look at segment AB, and if C is between A and B, and between means it lies on that segment, then we know that, say this is point C, then we know that AC plus CB equals AB. So the measurement of AC, which is a number, plus a measurement of CB, which is a number, equals a measurement of AB, which is also a number. Looking at the next proof, we're given that AB is congruent to CD, and we want to prove that AC is congruent to BD. If we look at that, it kind of makes sense because BC is congruent to itself, so we're adding the same amount to AB and the same amount to CD, so AB plus BC should equal BC plus CD. So let's look at completing this proof. As always, we start with the given. AB is congruent to CD, and that's given. We need to change that to an equality. AB equals CD, which is the definition of congruence. We have to bring BC into our argument. So we can say that BC equals BC, and that's by reflexive. Now I'm going to add BC to both sides of this equation right here. So AB plus BC equals CD plus BC, and that's the addition property. But we also know that AB plus BC is equal to AC. So that brings our AC, which we need right here, into our argument. And we also know that CD plus BC equals BD. And that brings our BD into the argument that we have going. And we know this by segment addition. Now I know that I can take the fact that AB plus BC equals AC and substitute that in for this. And I also can take the fact that CD plus BC is equal to this BD. So I'm going to do substitution. I'm taking step 4 and I'm replacing AB plus BC with AC. And I'm replacing CD plus BC with BD. And that's substitution. I'm taking what I know in step 5 and substituting it into step 4. I needed to prove congruence, so AC is congruent to BD, and that's by substitution. Okay, so this next proof gives us the given that AC is equal to the measurement AB, and that AB is equal to the measurement BX, and that CY is equal to XD. So reading through this proof, we use the first two given, AC equals AB and AB equals BX. From step 1, we have AC equals AB and AB also equals BX, so AC equals BX by the transitive property. Then we used our third given, CY equals XD, and to step 2, we added the same amount to both sides of step 2. So that gave us AC plus CY equals BX plus XD. This step, we're saying that AC, which is this right here, plus CY equals AY, and BX plus XD equals BD, and that's by segment addition. Substitution, because we're taking the AC plus CY and substituting that AY up into this step, and we're substituting this whole thing, BX plus XD, with the BD, and that's substitution. So this is a fill-in-the-blank type of proof. It helps to know what's happening, to read through it, to understand when I'm looking at the one step. Sometimes like this one, I can just concentrate on this one, and that's all I need to know. And I know that AC plus CY, looking at the picture, it makes sense that it's AY, and I know that because of segment addition. In the previous proofs, we always changed, if we needed to add something, we always changed congruence to equals and equals to congruence. Here, we're going to say that the properties, the reflexive, the symmetric, and the transitive, both apply to both equals and congruence. So it may not be necessary to always change a congruence to an equal sign. So reflexive would tell us that segment AB is congruent to itself. That if AB is congruent to CD, then CD would also be congruent to AB. And transitive, if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. So looking at our first proof, we're given that WY equals YZ. YZ is congruent to XZ, and XZ, let's do it on top of each other. Sometimes it's easier to see if we write it on top of each other. Then YZ is congruent to XZ. XZ is congruent to WX. Looking at what we were given, WY is equal to YZ, which basically means it's congruent, and YZ is congruent to XZ, and XZ is congruent to WX. So it makes sense to be able to prove what we want to prove here, that WX is congruent to WY. So let's change the one that's not congruent to congruence. So WY is congruent to YZ, and that's by definition of congruence. Then we have WY is congruent to YZ, and YZ is congruent to XZ. So we know that WY is congruent to XZ, and that's by transitive. And we can only do one transitive at a time. So now we have that WY is congruent to XZ, and XZ is congruent to WX. So we have that WY is congruent to WX, and that's by transitive for the second time. But we wanted it in the other order, so WX is congruent to WY, by the symmetric property. Looking here at this proof, we wrote down to the given that GD was congruent to BC and BC was congruent to FH. So that makes sense that GD is congruent to FH by the transitive property. So that gave us step 2. We used the remaining given, which was that FH is congruent to AE. So now we have that GD is congruent to FH and FH is congruent to AE. So that makes sense for the next step that GD is congruent to AE, but we wanted to prove it in the reverse order. So this would be symmetric because we flipped it around the congruent side. And that concludes our lesson 427.